Alright, hello everybody and welcome. My name is Mr. Raiden. This is my first foray into YouTube in quite a little bit. I have done some YouTube questions in the past, just as an extra source to facilitate what we're learning in class. My eventual goal is to one day digitalize my entire class, make everything online, practice problems, lectures, lessons, all of that, just as extra resources. That way my class becomes not just listening and less me talking and more students doing stuff and working together and practicing and such, and that's the ultimate goal. But I am not there just yet, and this is kind of a test case, we'll say, for some of the things I want to get to. So, in this video, we're going to be talking about the mole. We're going to be taking the first packet, kind of doing some practice problems. For now, my goal is to not give out lectures for every single little thing, but really just to go through some examples, worked examples of some of the practice problems. So I will call out, which examples we're doing from the packet. What page, what question, what number, letter, whatever it is. Just please note this video is being made in 2025, so if I've assigned or you're watching this video in a future year, the questions might be off just a little bit. But for now, we're going to get ourselves started here. This video is not meant to be a comprehensive view of the mole, but what it is meant to be is a comprehensive view of how we can do some of these practice problems. We're going to start our exploration on page 2 right here with question number 4, where we're going to be calculating the number of moles of oxygen atoms. So the first thing that we want to talk about is what is a mole? And simply put, a mole is a way to count stuff. And a mole is equal to 6.022 times 10 to the 23rd of anything. It is a counting system, and this is most commonly compared to a dozen, whereas if I have a dozen of something, that is equal to 12 of anything. And this can be any topic. This can be apples, bananas, atoms, eggs, elephants. Does not matter what it is, as long as it is that amount, it is a mole. And so what we're trying to do here is calculate the number of moles of oxygen atoms. And there's a few things that we just need to talk about before we get to. The first thing that we need to get to is this idea where we have a molecule versus an atom. That is going to help us understand what we are talking about. So here we have one molecule of carbon dioxide. It has one atom of carbon and two atoms of oxygen. And so what we can see here is that for every one molecule of CO2, then I have two atoms of oxygen. That's where we're going to start at, where one molecule of CO2 is equal to two atoms of carbon. And this is a ratio, this is a conversion factor that we're going to be using. However, what is important for us to understand is that we are just counting. Anytime that I have carbon dioxide, the amount of oxygen atoms will always be double it, always be 2 times. If I have 1 dozen CO2 molecules, right? If I have 12 molecules of carbon dioxide, then I'm going to have 2 dozen atoms of oxygen. It's always going to be the same ratio, 1 to 2. So we see right here, I have 12 molecules, or 1 dozen carbon dioxides, and if we count how many oxygen atoms are on the screen, we're going to have double it. Now, I cannot do the same thing with a mole, because a mole is a very, very large number, and I don't think I have enough computer space. But the same idea applies here, that if I have 1 mole of CO2, then that is going to equal 2 moles of oxygen atoms. 1 mole CO2, and we're talking about molecules in this case, but we can distinguish between molecules or atoms, doesn't really matter. Okay? And this is our first of our conversion factors that we're going to be using. 1 mole of carbon dioxide is equal to 2 moles of oxygen atoms. Every single time that I have a carbon dioxide, I have double the amount of oxygen. The example that I gave in class, think about a hamburger, think about a hot dog. Every hamburger I have has 2 buns to it. So if I have 5 hamburgers, I got 10 buns. If I got a dozen hamburgers, I got 2 dozen buns. If I have a mole of hamburgers, I have 2 moles of buns. It's always in that same ratio. The other piece of information that we need to understand is what a mole is when it comes to the conversion between molecules or atoms or anything and what a mole is. So we talked a little bit earlier that if I have 1 mole of CO2 molecules, and that is equal to Avogadro's number, 6.022 times 10 to the 23rd molecules of CO2. And so we now have all of the conversion factors that are necessary to solve this problem. We are trying to go from molecules of CO2, so we're trying to go from molecules, not moles, molecules of CO2, and we're trying to go to atoms of oxygen. But I cannot directly do this conversion. I cannot go from molecules of carbon dioxide to atoms of oxygen. The reason why is because we have to do an intermediary. We have to go from carbon dioxide to oxygen, which is that whole, hamburger analogy that I had just made. So we have to take a detour here, and instead of going straight from molecules of CO2 into atoms, the next thing that we have to do now is line up our conversion factors and get this to going. We are going from molecules, not moles. We're going from molecules of CO2 to moles of oxygen. But we don't have a conversion to go from molecules of CO2 to moles of oxygen. Think about it like this. When we have a compound, okay, if I have 5 grams of apples and 5 grams of bananas, that's like 2 different compounds. Apples and bananas are like having carbon dioxide and oxygen. We cannot compare the 2 of them. So what we have to do is use some kind of conversion in the middle, which thankfully for us, we have just done by talking about the hamburgers. We've converted between the 2 different compounds. We have figured out how we can connect our apples to our oranges. It's like the bridge that connects this together. So we can't go from molecules of CO2 to moles of O2. We have to instead go from molecules of CO2 to moles of CO2, and then we get to moles of oxygen. So we have to do a little bit of roundabout way to get this. So let's start this out here. My initial unit that I'm starting with is molecules of CO2. So I'm going to start here. I want to go from molecules of CO2 to moles of CO2, which is where we're going to be using our definition of what a mole is. We're using this equation here. Which unit am I going to put? Well, my unit right here is molecules of CO2. And whenever we do dimensional analysis, we want to put the unit on the bottom that matches the unit that I'm starting with. So right here, I now have molecules of CO2, which means that the other side of my conversion factor, which is 1 mole of CO2, and we don't need the molecules at that point, because it's just telling us we got a mole of CO2, will go on top. So that is my first step in my dimensional analysis. However, my unit is still carbon dioxide, which we want to get to oxygen. So I need to add another conversion. Our conversion here is going to use our hamburger analogy. I have moles of CO2 on the bottom, I have moles of CO2 right here on the top, so I need to have moles of CO2 on the bottom from my conversion factor. So I take this, I put this here on the bottom, And I would take my other conversion factor, 2 moles of oxygen, and this will go on the top. And now my moles of carbon dioxide on the top, moles of carbon dioxide on the bottom, and I can now solve for my equation. Alright, so let's resume here. You're going to see a lot of really fun screen transitions on my first go around here. Mathematically here, we have 6.5 times 10 to the 24th. Remember, when we're doing this, we're taking all of our top numbers, so 6.5 times 10 to the 24th, times 1, times 2, and we're dividing this by 6.022 times 10 to the 23rd. So I'm going to plug that out here into my calculator. Let's make it a little bit bigger here. We're going to get 6.5 E24 times 2. We're going to get this number, and I'm kind of skipping through the math here. I really should be doing this. No, let's do this properly. I'm going to do this in a calculator, kind of speak here. Times 2. I'm going to divide that by, well, my number on the bottom, 6.022 times 10 to the 23rd, and I'm going to get my answer, which equals 21.5875. We'll talk about sig figs. My initial number right here has 2 sig figs, so I should round this number up to 22 moles. Oh. I'm still learning the ropes here. Let's put this down here. 22 moles of oxygen. And that is how I get my answer. Alright, so for our next question here, we're going to be starting question 5 here. We're going to do letter D. I'm going to go right for that challenging one. So let's jump into it. Alright, now what we are dealing with calculating the number of oxygen atoms. So the question before, we went from atoms into moles. Now we're going to be going from moles into atoms. So it's kind of the same type of question, but in reverse. And we are given a starting value here of 5.0 moles of barium nitrate. The first thing that we kind of want to set off here is, what is our path going to be? And this is going to be a theme that's going to be common to this chapter, is setting up what path am I going to be doing? How am I getting from point A to point B to point C? We start here with moles of barium nitrate, and we want to get eventually to atoms of oxygen. I'll move that right out of the way there. Okay, so we cannot go from moles of barium nitrate directly to atoms of oxygen. Just like with our last example, we have to take a detour. And we have to use that intermediary where we have barium nitrate, which is our apples, and oxygen, which is our oranges. And so we have to go, our intermediary is moles of oxygen. And so instead of going straight there, we're going to go from moles of barium nitrate to moles of oxygen, from moles of oxygen to atoms of oxygen. And so let's start by crafting our conversion factors. I have my first conversion factor is between moles of barium nitrate and moles of oxygen. And just like last time with our hamburger analogy, we are going to look at our chemical formula. However, this time it's not as simple. So we're going to oversimplify just a little bit here. As my image magically appears on your screen here. We're going to talk a lot more about the structure of molecules, especially the nitrates there. But what is important to understand is that this is what barium nitrate looks like. And now we have a different ratio. This is one formula unit as the technical term, because this is an ionic compound, of barium nitrate. And for every one of these, this entire thing right here, we count up how many oxygens there are. 1, 2, 3, 4, 5, 6. Right? How do I also figure this out? Well, right here, my subscript being a 3 times my other subscript means that there are 6 oxygen atoms. And so this is kind of like, I don't know, let's call it a super hamburger, or maybe you go to McDonald's and get a 6-piece McNuggets. For every 6-piece McNugget meal that you get, you got 6 nuggets, kind of like that. You get 1 meal, 6 nuggets, always in that same ratio. If you got 12 meals, you'd have 12 times 6 nuggets. If you had 1 mole of those Happy Meals, you'd have 6 times a mole, 6 times Avogadro's number, 6 mole of those chicken nuggets. It's always in that same ratio. Okay? Our second conversion factor is, again, our definition of going from moles of oxygen, better yet not sign, into atoms of oxygen. And this is our definition, again, of what a mole is. Anytime I'm going from moles to something else, it's always that Avogadro's number. If I have a dozen oxygen, it's 12 atoms. If I have a dozen barium nitrate, it's 12 barium nitrates. It's always that same ratio. That 1 mole of oxygen is 6.022 times 10 to the 23rd atoms. And so this gives us our conversion factors to start with. Okay, and we could say that it's atoms of oxygen. I do just kind of cut off some of that because it's anything. It is technically, we're gonna be real here, it is atoms of oxygen. And let's move this over here so it's a little bit more clear, so we can squeeze this up here. So technically it is atoms of oxygen. Please just understand that it is cut off there. So let's start with our first conversion factor here. We're starting out with moles of barium nitrate, which means that we are going to be using this bottom conversion factor right here. Okay? The unit on the top that I'm starting with is barium nitrate, moles of barium nitrate. So this is the side that I'm going to take from this conversion factor. And I'm going to write this underneath here. Gotta make this nice. Let's see. Might not be able to fit. I'll make my line a little bit longer. Which means that my other half of my conversion factor goes on top, the 6 moles of oxygen. That goes right here. We're then going to go from moles of oxygen into atoms of oxygen. Alright? So let me just clear up our screen a little bit. And we can now fill in the rest of this. We need a new one here. My moles of oxygen is going to go right here. Goes on the bottom. My Avogadro's number of atoms is going to go on top. That way, when we're looking at our units, the moles of barium nitrate, moles of barium nitrate. Okay, I cannot cancel out moles of barium nitrate and moles of oxygen because they are 2 different compounds. It is like atoms, or apples and oranges. Moles of oxygen, moles of oxygen. Mathematically, I now have 5.0 times 6 times Avogadro's number. 10 to the 23rd. We can squeak that in right there. And when I put this up on our calculator here, 5.0 times 6 times 6.022 times 10 to the 23rd. We get this as our answer. We have 2 significant figures. Just keeping track with this. 2 sig figs. So my final answer should be 1.8 times 10 to the 25th atoms of oxygen. Okay? The next type of question that we're going to look into is how to calculate the molar mass of a molecule. And you're going to be given questions like this. You're going to be given examples where I'm going to give you the chemical formula of something, which practices what we've learned previously. And please just also note that I do ask you to include the units, because that is important to use correct units, which is what we're going to talk about. Okay? And where I wanted to start off this conversation is with the following example. So we're going to look at this example when we're talking about the counting, right? When we're talking about how many I have, 1 mole of eggs or 1 mole of elephants, they are the same amount. I can count them and say that I have the same amount. But that is not true of weight, or what we like to call mass. If I have 1 mole of eggs or 1 mole of elephants, the mole of elephants is going to weigh more. And that's because elephants weigh more than eggs. Think of it like this. If I have 2 feathers or 2 pieces of iron, which one is going to weigh more? The iron, because it's heavier. There's like that question where it's like, oh, which weighs more, 5 pounds of iron or 5 pounds of feathers? Well, they weigh the same. They have the same mass, but you're going to have a lot more feathers than you are going to have a piece of iron. And this is the same, this is also true for elements. So we can look at our periodic table, and we can see that there are different elements that have different masses, right? Copper, for example, has an atomic mass. Remember, this is from way back in chapter 1, 63.546. We go over one element to zinc, 65.38, right? The mass increases as we move through the elements. So the elements that have more mass, therefore, are larger. If I have 1 atom of hydrogen and 1 atom of krypton, the krypton weighs more. I have the same amount of them. I have 1 atom of each of them, but the krypton weighs more. And this is the same thing for a dozen hydrogen atoms and a dozen krypton atoms. I have the same amount of them, but the dozen krypton weighs more. And same thing with moles. If I have 1 mole of hydrogen atoms, that's going to be a lot lighter in terms of mass than 1 mole of krypton atoms. They are the same amount, counting-wise, but different masses. And as it turns out here, the atomic mass, perfectly helps us kind of understand the relationship between the mass of an atom and what is called the molar mass. So let's take, for example, this krypton here. What does this number mean? Now, when we talked about this in terms of atomic mass, we said, all right, well, the atomic mass is therefore going to be 83.798 atomic mass units. And in my slides, I go through a lot of the math that kind of goes around this, but let's simplify here. What this means is that if I have 1 mole of krypton, then the mass of those krypton atoms is exactly 83.798 grams of krypton. That's the relationship that we have experimentally found. And that's what the mole is defined, actually. It's the mass of a carbon-12 atom. Carbon-12 atom has exactly 12.0 grams if you have 1 mole of them. That's actually what we use to take that number. And what this means is that if each atom has a mass of 1.67 something times 10 to the negative 27th kilograms or something, and you have a mole of them, you end up getting straight back to where you started. And I put a question like this on your test, actually, and I realized that I should have added more significant figures, which is annoying because the answer that you got, or should have gotten, was not correct. But I digress. What is important here is that if we have a compound, we can figure out what the atomic mass, or the molar mass, is using the atomic mass of every single element that is involved in that compound. Okay? So let's start here with an example. We're going to start with carbon dioxide, which is a pretty simple example. Carbon dioxide has 1 atom of carbon and 2 atoms of oxygen. It looks a little bit something like that. And so to find our molar mass, we first have to figure out how much each of these atoms weighs. So we go to our periodic table here, and we're going to look for carbon, and we're going to look for oxygen. So carbon, right here, has a mass of 12.01, or 12.011. So for carbon, we are going to use 12.011 for our carbon atom. We're going to be using 2 decimal places for every molar mass here. And just to remind us, why are these numbers not whole numbers? There are different isotopes of carbon, carbon-12, carbon-13, carbon-14, and it's a weighted average. So there's a lot of carbon-12, not as much carbon-13, but overall there still are some carbon-13 atoms. So we're going to be using 12.01 for carbon. we look for oxygen, oxygen is 15.999. Now, we're not going to be using, when we round this up, right, for oxygen, it's 15.999. That 9 rounds up this, which rounds up that, which rounds up that. And so we can therefore use 16.00 for our oxygen atom. So let's get back into this now. Now that we have this information, okay, we said that carbon is going to be 12.01 and oxygen is going to be 16.00. So I have one atom of carbon, which is going to be 12.01, plus 2 atoms of oxygen, 16.00, plus 16.00. So if we bring up our calculator, which we don't need a crazy calculator for this one, but if we bring this up, 12.01 plus 16.00, and I am making, a note of, doing the 16.00. In your calculator, you can put 16. It's going to give you the same answer, but I'm just showing us when we're adding sig figs, we do want to keep those zeros there. And look, I even forgot a 0, just so that we're keeping track of our sig figs. So our final answer here is going to be 44.01. Now, before we get into the units of this, the way that I like to do this, instead of writing all this stuff out, because look, you want to write out 12 plus 16 plus 16 when you get to an example like that, 12 plus 12 plus 12. No. The way that we can do this is by doing just a little bit of algebra. What I like to do, all right, I'm going to cross this example out just so you can see the space here. I like to split this up by elements. So we start with carbon. We're going to do the number of atoms of carbon, which is 1, right? There's just the one carbon atom. Okay, we have one carbon atom, so that's where this 1 comes from, multiplied by whatever our atomic mass is, or our molecular mass, which in this case is 12.01. This would give us 12.01. And then for oxygen, we're going to do the same thing. Oxygen has 2 atoms of oxygen. That's from our chemical formula. So we're going to have a 2 here, and I'm just color coordinating here, show us where this is coming from. Multiply it by 16.00. Put that into a calculator. You can get 32.00, and then we just add them up. 10.44, and we get the same answer. And I'm going to tell you, do it like the second way, because when you get to an example like this, letter F right here, C12H22O11, a lot easier to do it the way that I just did it. All right. Before we move on to our next question, let's talk about the units of this. When we're talking about this amount here, I talked about this in the beginning. It is the amount of grams per mole. So if I have 1 carbon, like 1 mole of carbon atoms, okay, what this number tells me, let's say for oxygen here, is that if I have 1 mole of oxygen atoms, this becomes a mass of grams. And specifically, it has to be grams. And why we do this is because grams is something that we can measure. We can take, not of oxygen, it's a gas, but we can take an example, let's just say zinc. I can give you 65.38 grams of zinc. It is something tangible that we can use. And because of that, that's why we use molar masses, because it's something that we can measure. In the first lab that we did, we measured, the density of water and all that stuff, and you were measuring out, let's say 20 to 30 to 40 grams of water. That's in the scale of 1 to 2 to 3 moles. And instead of saying, look at all these atoms that we have 6.022 times 10 to the 23rd atoms, we can say that there's 1 mole, and this is how much it weighs, and it's something that we can very easily measure out. So our unit, going back to here, the unit is always grams per mole of a of a molar mass. And what this just means, just to put this into perspective for when it comes time to do conversions in a little bit, that means that there are 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. That is what this value represents. It is a way to go from mass, how heavy something is, to moles, how many of them you have. It is a way to compare, if I have 5 pounds of feathers and 5 pounds of iron, how much, counting-wise, do I have between them? If I have 5 apples and 5 oranges, I have the same amount of them, but which one weighs more? That is what the molar mass is used for. Okay? Let's do one more example, and just going to show us how we can, we're going to have to do some naming as well. So I'm going to give a few examples, or just show us one of these. All right? Let's do letter E, ammonium sulfate. And I have said before that we're still going to need a lot of the resources that we've used in the past. So let's bring that up. And look at that magic, and let's get started. So we're trying to find the chemical formula of ammonium sulfate. All right. One day, if you're watching this, not 2025, I'll have a video up on all this stuff too. I've done this in chapter 3 in 2025 or 24. But we can do a quick review here. Ammonium is right here, and the chemical formula is NH4+. Sulfate down here ends in 8, so it's one of these. It's SO4 2-. We have to do the crisscross method to get this chemical formula, so we're going to write out all of this, NH4 and SO4, and we're going to keep all this stuff here. We're going to take our charge, which in this case there is a 1 here, and so that imaginary 1 goes here, which means because it's imaginary, we don't have to write it. But this 2 is not imaginary, and it has to go here. But we don't have a 42, it's NH4 parentheses 2. And that gives us our final answer there, which we can then take back, find the molar mass. Alright, so we have NH42SO4. We have a lot of elements here, so let's break this down. We have nitrogen, we have hydrogen, we have sulfur, and we have oxygen. So what I'm going to do is we're going to start here. We're going to start by figuring out how many of each elements that I have. So we have nitrogen, we have hydrogen, we have sulfur, and we have oxygen. Okay, let's start by how many that we have. The nitrogens, now these are little colons, I like to keep myself a little organized here. There is 1 nitrogen here times the 2 of that outer subscript, which means that there are 2 nitrogen atoms. The 4 times the 2 means that there are 8 hydrogen atoms. The S, there's just 1 sulfur. And the oxygen, we just have 4 of them. That's our starting value for what we're going to be doing. That's all the information we're going to take from here. Right, let's look for those elements that we talked about. First one up was nitrogen. Nitrogen is right here. So what I'm going to do here, I'm going to write off what our molar masses are of each of them. For nitrogen, we are going to be using 14.01. That's 7 rounds up that 1. Next element was hydrogen. Again, we're going to be doing a little bit of rounding here. Hydrogen is going to be 1.01. Our next element is sulfur. We find sulfur in our periodic table. Sulfur is 32.06. And lastly, oxygen. If you listen to my last example, we know that this one rounds up to 16.00. So we're going to take these values and we're going to go plug them into our formula that I've already put on a different screen. Right, so a little bit of reorganizing later. Let's get into this. For our nitrogen, and I'm just going to have the calculator up here just to have it there. Okay. If you can do this math in your head, that's great. 2 times 14.01 gives me 28.02. Right. We take 8 times 1.01 gives me 8.08. We take 1 times 32.02, which gives me 32.02. 32.06, excuse me. And 4 times 16 gives me 64, and it is 64.00. That way, if you're doing with sig figs, when we add, we have 2 decimal places for all of them. We add all this stuff up, 22.02. Excuse me, 28.02 plus 8.08 plus 32.06 plus 64.00, and we get our final answer. I hit 61, so let's add an extra 3. We get our final answer of 132.16, and our unit here is grams per mole. Okay, and there's our example for ammonium sulfate. So the next thing that we're going to work on is converting between grams and moles, going from mass to moles. We spent a whole bunch of time doing by writing all these molar masses and all this calculation. So we're on page 5 right now. I plan to do, we're going to do letter A here. We're going to do letter F right here, and then we will do I would do letter K right here as well. So that's what we're going to be working on with these problems, okay? First thing to understand, anytime that we are going from grams to moles, or vice versa, going from moles to grams, okay? That is why I spent all that time talking about the unit of molar mass, because the unit of molar mass is grams per mole. So we have to go between moles, we have to go between grams, we have to use the molar mass. I've already solved for the molar mass of carbon dioxide. That's what I did in one of my earlier problems. So the molar mass of carbon dioxide, we said, is 44.01 grams per mole. Okay, so let's take this information out to my other screen. Alright, so right here, I rephrased the question. We have 88 grams of carbon dioxide, and we're going to convert this into moles of carbon dioxide. When I use the letters MM, I stand for molar mass, right? I'm not going to write out molar mass all the time. We have already found this value. But let's just remember what this means. This means that when we're talking about carbon dioxide, I have 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide, right? We talked a lot about the word per. Grams per mole is how many grams per for every 1 mole. And I'm specifying the grams of carbon dioxide because later when we start converting from one thing to another, just like our apples and oranges example we talked about earlier, we have to keep our compound stable. Okay? Because this is also a conversion factor, this can also be written, and I'm going to say it in the opposite way too. I have 1 mole of carbon dioxide for every 44.01 grams of carbon dioxide. I've just flipped it, just like you flipped your tiles. It's the same exact thing. So if I'm starting out here with 88 grams of CO2, and I want to convert this into moles of CO2, this is just a simple one-step conversion to do here, right? Now, we're going to take one of these, and actually I'm going to erase that line there. We have grams of carbon dioxide right here, which means on the bottom of my equation, I want grams of oxygen, or carbon dioxide, excuse me. Let's take that, get rid of that, goodbye, and put this now here. Why? Because I have grams of carbon dioxide and grams of carbon dioxide, and we end up with 88 divided by 44.01, which equals 88 divided by 44.01 gives me that. We have 2 significant figures, so we are going to round this up to 2.0 moles of CO2. Alright, let's take another example where we're going to be having to do some extra type of conversion. In addition, we're going to have to find ourselves a molar mass. So we're going to be doing letter F here. Letter F has everything. We have to find the compound, we have to find the molar mass, and we have to do a conversion. So let's start by finding the chemical formula of silver oxide, right? If we kind of think way back to some of the things that we've talked about, silver right here was one of those that you had to memorize the charge of. We had the +1, we had the +2, and just a reminder, +3. We have that little line there. So we're making our formula. We have silver, that is a +1, and oxygen is right here, -1, -2. So oxygen is a -2 charge. It is oxide, right? We do our crisscross method. We are going to end up with Ag2O. That's our first step, is finding our correct chemical formula. Step number 2, find the molar mass. We're on this screen. Let's do it right here. Our first element is silver. We have 2 silver atoms, and our molar mass of silver is a large number up here. It is 107.87. Right, we add that together, and we get 2. I'm going to do this off screen here. 107.2 times 8, 107.87 times 2 is 215.74. And my oxygen, we have 1 oxygen atom. Hopefully by now we are remembering that oxygen is 16.00, which is just 16.00. And if we add these values up, 215.74 and 16.00, we add this up, we get 11, carry the 1, 231.74. We're going to slap that unit on there, grams per mole. Alrighty, so our goal here is to convert 0.45 milligrams of silver oxide to moles of silver oxide. And I emphasize the milli because my unit of molar mass is in grams, and my unit of mass that I'm given is in milligrams. Therefore, I must do a conversion. And I will have you memorize this conversion factor. Okay? There's 2 that I'm having you memorize, milli and kilo. And you're going to have to remember it. 1,000 milligrams is equal to 1 gram. So the first thing that we should be doing right here is taking 0.45 milligrams of Ag2O, or silver oxide, and converting this into grams. And we could say, alright, it's grams of Ag2O. I'm just being a little lazy, but I will be unlazy. And that cancels out here and here. So we can continue this. We can add more to this, because now my unit is grams of silver oxide. And now it is in grams, which is what we want it to be. So let's take this and let's move this over. So we're going to need a lot more space here. And now let us use our molar mass, reminding us that what this is telling us is 231.74 grams of Ag2O is equal to 1 mole of Ag2O. So, which one am I going to choose here? Well, I have grams of Ag2O right here. So we're going to take the grams and we're going to put it right here on the bottom. We have, since our other one goes here on the top, we're going to keep track of our units here. The grams of silver oxide cancel out. The grams of silver oxide cancel out. Mathematically, what this equals is 0.45 times 1 divided by, I'm going to put this in parentheses here, 1,000 times 231.74. So let's put this one in my calculator. We're going to get 0.45 divided by, because it's just, we don't ones, 1,000 times 231.74. Close my parentheses, and we get this as our answer. We started out with two significant figures, so our answer, again, should be two sig figs. 1.9 times 10 to the negative 6th. What unit am I left with? It's right there. Moles of Ag2O. So that is going from grams, or going from mass into moles. What about if I'm going from moles into mass? So let's do one quick example with that, because by now it's the same thing. But we just have to do a little bit of conversion sometimes. Alright, so let's go bottom page 5 here, question 2, which is going from moles into grams. Let's do letter K here. I picked letter K because we already found the molar mass of carbon dioxide. We've done it now 3 times. 44.01 grams per mole. Right? For each one of these types of problems, if you are converting, like I said, from grams to moles or moles to grams, you need a molar mass. Anytime I do one of these conversions, I need a molar mass. Okay? So if I am starting here with 16 millimoles, that's not my unit there. That's a mole, not a millimole. So we have to do that conversion first. Okay? So let's take this out to the paint dock. Okay, so ignore my little grammatical errors there. We're starting out with 16 millimoles of carbon dioxide. I've already found the molar mass. I told you you need to have it anytime that we're doing one of these conversions. But like I said, we have to convert this into moles away from millimoles. And because it's a milli, it's the same exact thing. 1,000 millimoles of carbon dioxide is equal to 1 mole of carbon dioxide. That cancels out the millimoles. We now have moles of carbon dioxide, which is good. That is what we want. Let's move this over so we have space for all of this. Right? Reminding us of what a molar mass is. It is how many grams that there are of carbon dioxide for every 1 mole of carbon dioxide. So when I need to solve this, the unit that I have on the top is moles of carbon dioxide. So I'm going to put moles of carbon dioxide on the bottom here. And I'm going to put the grams of carbon dioxide on the top here. And this way, moles of carbon dioxide cancels out with each other. What am I left with? 16 times 44.01 divided by 1,000. Okay, we bring up our calculator again. 16 times 44.01. I'm going to take that answer, divide that by 1,000. And I get this as my answer. We started with 2 significant figures, the number 16, which means my answer should be in 2 sig figs, 0.70 grams of CO2. How do I know it's grams of CO2? Look what I'm left with. It's the only thing I did not cross out. Okay? We're going to be using this type of conversion throughout the rest of this chapter, and for a good chunk of this the year as well. Right? We got 2 more types of questions coming up. We're going to talk about concentration, and we're going to talk about what a hydrate is. So we can think about concentration in terms of salt water. I have my cup here. Now, this is pure water. If I added a pinch of salt, I would probably taste it. It would be a little salty. But if I took an entire spoonful of salt and added this to my cup, I would try to drink it and it would be disgusting. Okay? Why? Because there's more salt per volume. Okay? The more salt that I add, the saltier it is. We call this concentration. And the unit of concentration that is most often used in the chemistry class is something called molarity. And as the term implies molarity, it includes moles in it. And this is our formula. And the capital M is concentration, but also molarity. And we use a unit capital M. And if something is 5.0 M, we call that 5.0 molar. That's kind of just the terminology of it. So it's a 5 molar solution or something like that. The N at the top there is the moles of the solute. And that term solute just means what is being dissolved. In other words, what is aqueous? The aqueous thing is the solute, and the solvent is the water. It's what you dissolve it in. We're always going to have water as our solvent in this class. But that means that the moles of solute is whatever we're dissolving. It's the aqueous thing, and it's how many moles there are. And the volume is how much liquid we have, and the units are going to be in liters. So a 5 molar solution of sodium chloride would have 5 moles of sodium chloride in 1 liter of water. And we can use this formula and our conversions between grams and moles that we just talked about to create concentrations of aqueous solutions. I'll just give you an example of this. When we did our double replacement lab, I had to specifically calculate what mass I needed to create specific concentrations of our solutions in our lab. That we're not just throwing random amounts in. I did do those calculations, and I did the same calculations as you're about to do. Okay? So let's get started. Alrighty, so let's start here. First thing that we're going to be doing is solving the concentration formula. We talked a lot about solving formulas. Let's do this again. The formula right here that we're using is that the concentration is equal to the number of moles divided by the volume. Okay, and I'll just remind us that this is N is the aqueous thing. The aqueous moles. Okay, and the volume is equal to the volume of water. We're always going to be using water in this class, and it's going to be measured in liters. So something that is 5 molar is 5 moles per liter. That is what our unit means. 5 molar is 5 moles per liter. That's the concentration unit that we're going to be using. Okay? Let's solve this equation. M equals N times V. We're going to solve it for N. We're going to multiply both sides of my equation by V right here. The V's cancel out. I've already solved it. V times M equals N. Right? On the other side right here, if I have M equals N divided by V, and I want to solve for the volume, I'm going to do the same steps. Please don't do this. N times N is N squared. I've harped about that a lot. Please don't do it. It kills me every time I see that. Multiply by V. Okay. That cancels out. We are left with the same thing. V times M equals N. We're going to divide both sides by M. Cancels this out. V is equal to N divided by M. And that's what we're going to be using for the rest of this. Okay? So I'm going to have these formulas. This is where they come from. I'm going to be using this for the rest of these calculations here. Okay? So let's start here. We'll start with letter A. Okay? Important. 6 moles of sodium chloride is dissolved in 0.500 liters of water. Reminder, V is equal to my volume of water, and N is the number of moles. So therefore, the concentration is just going to be the number of moles, 6.00, divided by the volume, 0.500. If you want to keep track of everything here, I've written this out, right? Keep track of your variables. M, well, that's what I don't know, because that's what we're trying to find. I'm telling you that V, that's my liters. You need to know that liters measures water, or volume, excuse me. I'm not telling you it's dissolved in a volume of 0.500 liters. You have to know that a liter measures volume. It's just kind of there. And obviously moles, which is N, is just 6.00, right? We do this math, dividing by 0.5 is the same thing as multiplying by 2. We're going to get 12.0, simplifying here. That is my unit, or that is my value. We have 3 significant figures. Now, what unit can I use? You can use capital M. That's perfectly fine. If you would also like to, you can use 12.0 moles per liter. Moles per liter. Let's do that. Running out of space. Those are the same thing. I will probably use the capital M to talk about molar, but it's 12.0 moles per liter. It's the same thing as 12.0 molar. It's how we say things. Okay? Question B right here is the same exact thing, except I have changed one little word. I have changed it from grams to moles. Nowhere in this formula do I ask about grams. But we've spent a lot of time going from grams to moles. And whenever you see I have to go from grams to moles, your brain has to start going off that you have to find a molar mass. So let's find the molar mass of sodium chloride. Okay? We go back here. Sodium chloride. Sodium is right here, which means it's a +1. Chloride is a -1, and our chemical formula is just NaCl. If we put this on the big screen, we got one of each. So our sodium is 1 times 22.99 for our sodium. And our chlorine is 1 times 35.45. I trust that we can do this, right? Multiplying here. I'm just going to simplify this on my hand calculator that I got up here. I got the same calculator as all of you that I have at home. I get 58.44 grams per mole. That's the value that we're going to take over. 58.44 grams per mole. That's going to help us do a lot of these conversions. Okay? So, our molar mass is 58.44 grams per mole. Now, if we're looking at this question, everything is the same volume, okay? But the molarity is going to be a lot different. Because I don't have 6 moles. I have to find out how many moles I have. The first thing that we have to do is convert from 6.00 grams. We got to use our molar mass right up there, right? You want to, if you're confused where this is coming from, I do suggest you do some of the prior questions. All right, and this is NaCl. I should be a little bit more better with my labeling. Sorry. 1 mole of NaCl. Grams cancels out. Grams cancels out. I put this off into my calculator here. Let's see, what do I get? I end up with 6.00 divided by 58.44. I get this is my value. Now, when it comes to the significant figures, don't round this yet. We're going to keep this number in our calculator stored. Or just, we're going to keep it in the back of our mind. You know what? Realistically, you could write this out here as 0.102669. You don't got to do everything. But we're not going to round yet. Because this is now my unit of moles of NaCl. Oh, we ran out of space there. I'll hide myself. Right, we got that amount of moles of NaCl. And now we have to take that amount of moles, and that is what goes here. 0.102669. And so now I'm just doing the same thing that I did in the prior question. I'm doing the same thing, except my formula, right? I'm going to put this down here in the corner. My concentration is equal to my moles, 0.102669, divided by my volume, which is still 0.500. I can put this into a calculator. Let's bring this calculator up and over. I'll show myself again. 0.102669 divided by 0 or 0.500. And I get this as my value. Now, when we talk about sig figs, we have to go back to the original value. This 6 grams right here, 3 sig figs. Right where I'm writing. 3 sig figs. That is also 3 sig figs. So my answer should have 3 sig figs, 0.205. My unit is molar, or moles per liter, whatever you want to write. I can write moles per liter as well. Doesn't matter. So there's just an extra step there. That is 2 extra steps. Similar type of question, a lot more involved here. Okay? That's the only 2 that I'm going to do out of this section here. The rest of this here, these questions here, this is the same thing as A, but I made one very slight difference. Milliliters. Milliliters. Why? Because molarity is moles per liter. So I have to convert from milliliters into liters. I have to convert from milliliters into liters. I have to convert from kilograms to grams. Remember, we said it was 58, I think, 0.44 grams per mole. Kilograms and grams are different as well. You have to be aware of the units, and they have to match, or else you're going to get the wrong answers. Right? Let's come back. We're going to look at one of these different type of concentration questions. Alright, we're scrolling down. We're on the next page here. What is this? Page 7 here, right? Let's bring up that formula again. That's going to be our starting point. We have that, M is equal to N over V. And we solved, and we said that V times N equals N. And I'm just recapping what we talked about. V is equal to N divided by capital M there. Just recapping what we talked about. Let's look at what question 3 and 4 are asking us for. 3. Calculate the number of moles dissolved in the following aqueous solutions. I have a 5.00 capital M, or moles per liter, solution of sodium chloride dissolved in 15 liters of water. So if we're going to look at all my variables, V, M, and N, 15 liters, that's my volume. My concentration is 5 molar. My N, don't know what it is. Look what I'm trying to solve. Alright? Luckily for us, we've already solved for the formula. We did that right here at the top. Say that V times M equals N. Let's plug in those values. 15 times 5.00. We can put that nice and easy into a calculator and get our value. We have 75. We got 2 sig figs on the 15. 2 moles of sodium chloride. That's it. Why do I not need a molar mass here? There's no grams. Molar masses are for grams. I don't want grams. It's not involved here. So that's question 5. Questions B and C are the same exact thing, but just like I talked about with the last question, milliliters has to be converted to liters. And I'm going to give you questions that are in milliliters. I'm not going to mention that you got to convert it to liters, because you have to know that your units have to match. It's going to be a reoccurring theme, is that you're just going to be given units and have to read carefully and recognize that I need to convert them. Okay? Question 4. Calculate the volume of the following aqueous solutions. So we're going to use our volume formula that we have solved for. Now, volume is equal to N divided by M. Look at A. A 5.00 molar, right, that's our M, of sodium chloride is created with 0.055 moles of sodium chloride. There's my N. Okay, nice and easy. Right. My volume here, or my volume would just be 0.55 Missed a 5 there. Divided by 0.500. So I can just do this math real quickly. My unit here, my volume, I have how many sig figs? I have 2 significant figures. That is 2 sig figs. So my answer right here is 0.11. What is my unit? Well, moles per liter. Have to be in liters. Liters of water. That's the volume of it. Okay? Letter B. I have a concentration. I have an M. I don't have moles. I have grams. And this is more realistic. Realistically, you're going to be measuring how much salt. Okay? How much salt do I have? I'm going to mass it out. I'm going to put it onto a scale, and then I'm going to, add it to my water. We base it off of the mass. So I have to do that conversion myself to find the concentration. So if I'm giving you grams, I need to go from grams to moles, and those alarm bells better start ringing that I now need to find a molar mass. I made every single question here sodium chloride. It's the same. I talked about 58.44. So let's do this problem. Here, let's keep our formula. V is N over M. We talked about the molar mass of sodium chloride is 58.44 grams per mole. So what is the volume of 2.05 molar solution containing 18.9 grams of sodium chloride? We have to convert that into moles to fit our formula. Okay? So 18.9 grams of NaCl. I'm speeding through a lot of this. I'm going to put grams here on the bottom. 58.44 grams of NaCl. 1 mole of NaCl. Let's bring up the calculator again. Let's move it up and away. 18.9 divided by 58.44. This gives me this value. I'm not going to round this just yet. It's equal to 0.32340. We'll call it 9. We'll round it there. Moles of NaCl. Grams cancels out here. Now I can use my volume formula that I solved for. Turn the calc back on later. My volume is the moles, which is 0.32, this whole big number. Ran out of space, but you get the idea. Divided by my concentration, which is 2.05. So we bring back the calculator. I'm going to take this number, divide it. By the way, the ANS is the answer, which is the previous example. If you don't touch anything on your calculator and you just press an operation key, it'll bring up the answer, which is the last number that I just did. So, useful calculator tricks. Right? Now I'm going to worry about the significant figures. I have 3 sig figs on both of my starting values, 2.05 and 18.9. So my final answer is going to be 0.158. What is my unit? Concentration is measured in moles per liter. Has to be liters. Has to be liters. There's a chance in the future I might ask you a question like this and I say, give your final answer in milliliters. And you're just going to have to do an extra conversion at the very end. Okay? Rest of this question, question C, is a little bit more word problem-y. But more importantly right here, milligrams. I can't go from grams, milligrams to moles. It's got to be, right, grams per mole. That's what a molar mass is. So I got to do milligrams to grams. I have to do that conversion, right? And this, by the way, is types of questions that I've done. More like question 5, but, what volume of water is needed? You want to make a certain concentration of a solution. Okay? Question 5 right here is the same thing as question 3. Calculate the number of moles. But then you have to do the extra step of converting it to grams. That's the one extra thing, right? How many grams of sodium chloride I needed to make a 2.0 liter of a 0.400 molar solution? This is the same exact question as this. Not mathematically wise, but conceptual wise. It's the same steps as what I've already done, and then you get an answer in moles, and you have to convert it into grams. Same thing. So we said that N is M times V. Watch that if you want to know how I get there. So my volume is 2.00. My concentration is 0.400. Right? I multiply those two together. I get 0.800 moles. Not what I asked for. I asked you for grams, so I'm going to do this one conversion just one final time. 58.44. Found the molar mass several times by now. Grams of sodium chloride for 1 mole of sodium chloride. Got the old calculator. 0.8. 58.44. Enters. I start out with 3 significant figures, 46.8 grams of NaCl. That's the type of question that I have done when I've prepared solutions. When I made solutions for all of you for our labs, that's the type of math that I did, because then I took a balance, a scale, and I measured out 46.8 grams of sodium chloride. Okay? Questions B and C are the same idea with just a little bit of extra steps here. Number one, I have finally moved away from sodium chloride, so you got to find the chemical formula and the molar mass of silver nitrate. So there's a few more steps involved here. You have to convert from milliliters into liters. All right. Question C has a whole bunch of things. You got to find this chemical formula. Okay. You have to go again from milliliters into liters. And then you're going to get a final answer. You're going to get your answer in grams, and then you're going to have to go from grams into milligrams. Because I asked you for it. You get your final answer in grams, and then at the very end, you have to convert it into milligrams. So there's a whole bunch of just different things that I can throw at you. I can make you do a conversion at the beginning, at the end, right? I can make you find a molar mass. I can give you a scientific notation. There's a lot of possibilities that you have to think, work around and keep track of what is needed. These questions add layers, every single one of them. That is how I designed this handout. Is that every single A to B to C adds something new, whether it's a conversion or something. All right. We have one final topic that I'm going to talk about in this video. I know this is already a long video, but I like to yap by now. The last thing that we're going to talk about is a hydrate. So let's get that up onto the other screen. So hydration is good. I like to be hydrated. I have my water with me at most times. Term hydrate. To be hydrated means you have water, and that is no different. But what a hydrate is, it is a compound that has water as a part of its structure. It is a solid, a powder that has water in it, right? And we call this a hydrate. Without the water, it's called anhydrous. Just add that here. The way that we design this and say this about this, we use this little dot sign right here. It's not a multiplication sign. It's just the formatting that we do. And there's how many waters there are. And then we call it the name of the compound. And then we use the prefixes. The mono, di, tri, whatever, etc. And we use the term hydrate. So I'm hiding the cover of this, but this is barium chloride, BaCl2, and there are 3 water molecules. So we call it barium chloride tri meaning 3, trihydrate, right? And this idea is that when we add water to something that's anhydrous, and the word the prefix an means without, so with anhydrous is without water, is we can have a color change like this. And what we are going to do is do that in reverse. We're going to evaporate the water by adding, fire, and we are going to calculate what the hydrate number is, how many waters there are. And we can do this by looking at ratios of moles. Look at that. That's what we started this whole thing with. Ratios of moles. We did that before. Right? When we calculate the molar mass of a hydrate, you just do the same thing, but you have to include water. There's 3 waters. Water's got 18.0, and I really should have an extra decimal place here. Oops. You just have to add the water to it. How many waters you got? Right? This is what we're going to be doing. You're going to get a sample of copper sulfate. You have to calculate experimentally what that X value is. Alright? So let's take an example here. I'm going to walk you through all this stuff in class. Let's get back to one of the examples in the packet. Alright, our final question had all of this stuff that we have done. Finally to the very end of this question. So, let's look at this example here. I got a sodium sulfate.x H2O. So what I'm going to do, I'm going to take this, I'm going to copy this, put it into my paint compound, and let's get to it. Here's the first thing that we have. We have a sample of hydrated, meaning there's water in it, of sodium sulfate, right? And when it is a hydrate, we have 0.386 grams of sodium sulfate at X H2O. And what we do, I just ran out of space. What I'm doing, or what we're going to do, is we're going to take that and we're going to heat it up and evaporate the water. And after we've evaporated the water, because there's less water, the mass will decrease. That water has a mass, becomes a gas that goes and flies away, and my mass decreases. And I end up with 0.170 grams of just Na2SO4. And so I lined this up here to show us that if we take these two values and subtract them, okay, and we get, what, 214? Yeah, 0.214 grams. That's how much H2O there is. Okay? We can figure out how much water burned off because it's the difference. But when we have grams of one thing and grams of another thing, it's like comparing apples to oranges, which I've been talking about for several times throughout this video, which means that we need to convert it to moles. We have to find out how many waters there are per sodium sulfate. We need to go to moles. So what I'm going to do, find these molar masses and convert them. Okay? I've done several examples of molar masses. Please pause the video, go back, do this problem. I'll give you a few seconds. Find the molar masses of sodium sulfate, Na2SO4, and of water, because they're going to be on the screen in a few. Okay? Alright, and there they are. So, we have to convert both of these values into moles. So, we've done a lot of conversions right here. Let's do this. We have 0.170 grams of Na2SO4. We multiply that by the molar mass, 142.04 grams of Na2SO4. Squeezing that 4 there. 1 mole of Na2SO4. Bring up the old calculator, and we get, put it into the other corner, which shows up, 0.170 divided by 142.04. That is our value, and we are ending up with 0.00. See, now we'll do sig figs here. We got 3 sig figs because we're going to be dividing this. 120 moles of Na2SO4, and let's squeeze in 0.214 grams of H2O times 18.02 grams of H2O, 1 mole of H2O, and we put this into our calculator, 0.214 by 18.02. This gives us this value right here, which is 0.0119 moles of H2O. So all that's left now is to make a ratio of moles. When we make this ratio, what we're saying here is that for every 0.00120 moles of Na2SO4, I have 0.0119 moles of H2O. And if we just wanted to divide this, okay, well, how do I figure out what am I dividing? How do I figure out what I'm dividing? Think about it like this. You're always going to have more water than the sodium, than whatever you're starting with. A trihydrate, a pentahydrate, a hexahydrate, right? What does that mean? We should always kind of divide by our smaller number so we get whole numbers. So to find our ratio, we are going to take our smaller number and divide it by the other one, 0.00120. We're going to put our smaller number on the bottom. This is just going to give us a nice, neat whole number. We're going to put this into our calculator, 0.0119 divided by 0.00120, and we get this answer. You're always going to round to the nearest whole number, so we're going to have 10 waters. So our final chemical formula, okay, our final chemical formula is going to be, I'm going to erase this and I'm going to write it all out. So with our 10 here, we have Na2SO4 dot 10 H2Os. What are we going to name this? Well, this is sodium sulfate. We have to include the prefix for 10, which is deca. We call this a decahydrate. Alright? I have not quizzed you in the past, like repeatedly, on going from the formulas to the name, so I'll probably sneak it in somewhere for you, or give you something where you don't need a Roman numeral, just because I haven't kind of kept you up on that. Alright, finding the molar mass of this hydrate, you just have to do, you found the molar mass of that, and you have to do the molar mass of water, which I remember is 18.02, multiply it by 10. You just add them all up. Okay? So, my goodness, this has been a long video. If you have stuck with me through all of this, thank you for watching. I do hope to eventually do more of this. This is a relatively kind of general overview of each of the types of questions. You kind of just have to practice this. So I wish you the best of luck with the rest of your studies, and have a wonderful rest of your day wherever you are watching this.